Okay, the first lesson in the Relations and Functions unit is really called Picture Patterns. We're using patterns to basically get into more details about relations and functions. You've already learned in junior high about relations. Now we're extending into what a function is. It's a particular type of relation, and some more specific properties of relations. So take a look at the first set of diagrams here. It says the three figures shown below left show cubes made from toothpicks and marshmallows. So just imagine that those circles are marshmallows and the lines are toothpicks. In this investigation, you'll examine the relationship between the number of cubes and the number of marshmallows. Draw the next picture of 4 cubes by completing the picture on the above right. So we've started this for you. So basically, I'm just going to kind of freehand here, kind of going to freehand here. Actually, I want it to be blue, so let's do this. So line there, marshmallow, marshmallow, line, marshmallow, join up, down, like that. Okay. So now that has basically 4 cubes together. So here, this is 1 cube, this is 2 cubes, 3 cubes, 4 cubes, and we can keep on going. So there is a relation between the number of marshmallows and the number of cubes. In this situation, the number of marshmallow doesn't need to be there, depends on the number of cubes to be made. Therefore, we say the number of marshmallows is the dependent variable, because it depends on how many cubes, right? If you don't know how many cubes, you don't know how many marshmallows. And what it depends on, the number of cubes, is the independent variable. So you may have learned those words before in this context, but they might be new to you, and those we will use throughout high school math. The relation between the number of marshmallows and the number of cubes can be represented as a table of values. In a table of values, the independent variable is always in the first column and dependent is always in the second. We often use a single letter to represent the variables. So here's a chart that we've made for you, a table of values. Use the diagrams above to complete the first 4 rows of the table of values below, stating the number of marshmallows needed to make the given number of cubes. So let's take a look here. So count them up. Basically, if you think about it, it's 4 in the front and 4 in the back. So there's 8 marshmallows. So when you add on a cube, you've already got these 4 marshmallows on the side. So you're really adding only 4 more. So that would be 12. And so then you've got this, and you're adding on another cube, which only requires 4 more marshmallows. So that's 16, and this would be 20. So you can see a pattern is each time you add a cube, you add 4 marshmallows. Okay, so number of marshmallows to start was 8, and then we had 12, and then 16, and then 20. So we're calling the number of cubes C and the number of marshmallows M. So this is the independent variable, and this is the dependent. As it says in dependent, okay? As it says, usually best form is to put the independent first in a table of values. Doesn't have to be, but that's sort of commonly what's done. Examine the pattern of the numbers in each column. Complete the last 2 rows of the table. So we're just adding a new cube each time, and as we found the pattern, we're adding 4 each time we add a cube. Okay. The relationship between the number of marshmallows and the number of cubes can also be represented as a set of ordered pairs. In each ordered pair, the first element is always the independent variable, and the second is always the dependent. The ordered pairs are enclosed in a set of brackets like these. I call these squiggly brackets. Technically, they're actually just called brackets, and then the round ones technically are parentheses. But in math, I just call those squiggly brackets or set brackets because they're used for sets of numbers. So mathematically, you could call those set brackets. And then these are like ordered pair brackets. Complete the following set of ordered pairs that represents the relation between the number of marshmallows and number of cubes in this situation. So we've got 1 cube, 2 cubes, so we just go in order, 3 cubes, 16 marshmallows, 4 cubes, 20 marshmallows, 5 cubes, 24 marshmallows, 6 cubes, 28 marshmallows. Of a relation is the set of all of the first elements of the ordered pairs. So you may have learned this before, but you might not have. Probably you haven't. In any case, all it is separating the independent values from the dependent values. So domain is for all the independent values. Sometimes it's specific values, like in this situation. Sometimes it's all the real numbers between 1 and 10. So it's an infinite number of values. In this case, it's what we call discrete. It's natural numbers. We can get them from the first elements of your ordered pairs or from the first column of your table of values because those are the independent values. So all you do here is list them. Notice how they're separated by commas because, as I said, they're discrete values, but they're in those set brackets, those squiggly brackets, and it's capital D equals. Okay. Order of the elements does not matter. In this case, no reason to mix them up. So keep them in order if you can. Okay. The relation between the number of marshmallows and the number of cubes can also be represented as an arrow diagram. So we've talked about a table of values, a set of ordered pairs, and now something that might be new is an arrow diagram. The elements of the domain are written vertically in an oval on the left. So these are the domain values here, right? So domain values. And so they are the independent values. And the range are written vertically in a second oval on the right. So domain, and the other word we use is range values, okay? And those are for, so range values, which are for dependent values, and they're on the right. Arrows pair each element in the domain with its corresponding range value. If the elements of the domain and range are numbers, they are generally written in order from the smallest number at the top. Complete the arrow diagram that represents the relation between the number of marshmallows and the number of cubes. So in an arrow diagram, it is important to list your domain values in order, lowest to highest, range values in order, lowest to highest. And if they don't match up that way, so if a domain it actually gives you the smallest range, then your arrow is going to go diagonally, but that doesn't matter. In this case, this is pretty straightforward, right? We're going to fill in with our range values, our second column in our table, and then these just match up across. Okay, so for a domain of 5, we get a range of 24. Domain of 6, a range of 28. So the arrow just goes to what the range value is for that particular domain value. Then another method is to graph. So the relation between the number of marshmallows and the number of cubes can also be represented as a graph, where the dependent variable is on the vertical axis. So this is always dependent, always. And this is always independent here. Okay. Draw the graph that represents the relation between the number of marshmallows, number of cubes. Label the axes. Note that the scales on the two axes do not have to be the same, but they have to be equally spaced within each. So here we're going to go up by 1s for our domain, but we're going to go up by 4s for our range, as long as we're consistently going up by 4s. So here, we're not going to call this range. We're going to, for this particular example, this is the number of marshmallows. and then this is the number of cubes. Now we need to finish off here. So 5, 6. We just went to 6, so we'll leave it. And then we went 16, 20, 24, and 28. Okay. Where do we go? Sorry, did we go to 7? No, we went to 6. Right. Okay. All right. So now we're going to fill those values in. So our first ordered pair is 1, 8. So we're going to graph that. Just plot a point. Then it was 2, 12, and then 3, 16, and then 4, 20, and then 5, 24, and then 6, 28. Okay, notice how they form a straight line. So this is actually called a linear relation because it forms a line. And we'll talk more about that. You've done some relations lots in junior high. Okay, so we've got that done. Before we do any more with the graph, it says you probably noticed that the points you plotted all lie on a line. Should you connect the points with a line? By connecting the points means that every point, including the ones between the points you plotted, makes sense for the situation. So it says, note that the line passes through 1.510, which means that you can make 1.5 cubes with 10 marshmallows. Does that make sense? No. Okay. So should they be connected? No. So sometimes our relations are connected. Our table of values or our ordered pairs are just a sampling of all of the values that represent the relation. Sometimes we don't. We cannot join these up. Okay. Now you might join them up in order to answer more questions. Like if you wanted to know how many marshmallows for 10 cubes using a graph, we'd have more graph paper. We could extend this out to where you get x equals, or the independent equals 10, look across, get the dependent, and that would be good. So you actually joined up the line, but the values in between don't make sense. So unless you're doing something like that, just leave it without them joined up. So if it makes sense for the points to be connected, then we say the data is continuous. If it does not make sense for the points to be connected, then we say it's discrete. In this situation, the data is discrete. And I already used that word a little bit earlier. And therefore, the points should not be connected. Number 9, examine the values in the second column of the table. You may have noticed that the pattern in the second column of the table of values is to add 4 to the previous number. What if you wanted to determine how many marshmallows are needed to make 56 cubes? One way to determine the answer is to keep adding 4 until you get to the 56th row, but you probably don't want to do that. Instead, it may be better to find a rule that relates the number of marshmallows to the number of cubes. Examine each row of the table to find a rule that relates the number of marshmallows to the number of cubes. Check to see that the rule works for other rows in the table. Write the rule in words by completing the following statement. So to determine the number of marshmallows needed, so this is your dependent, take the number of cubes, that's your independent, and what do? Well, let's take a look here. Actually, I'm just going to go back to the table. I always kind of like to go back to the table. Okay, so what I always say is take a look here. If these are increasing by 1, this is increasing by 4, right? So for every 1 increase in C, this is increasing by 4. Okay, so these basically match up in a sense that you have to multiply your number of cubes by 4, and then that would give you, so let's test out what that gives you for each of these C values. So 4 times 1 is 4, but we need to get 8. So now we need to add something. So a linear relation will always have a linear term, which is basically a multiple of the C in this case, and then something added or subtracted. It's never going to be squared or cubed or divided by C if it's a linear relation. And we already know it is because it's a straight line. So let's check for 2. 2 times 4 is 8, but we need 12. 4 times 3 is 12, but we need 16. So each time we're 4 short. So we need to add 4 to that. Okay, so our rule then, take the number of cubes and multiply by 4, and then add 4. Okay, so we don't add 4 first and then multiply that result. We need to multiply by 4 first and then add 4. So order matters. Relation between the number of marshmallows and the number of cubes can also be represented as an equation. Use your algebra skills to translate your rule above from English to math. Okay, M is marshmallows, C is cubes. So the number of marshmallows is equal to 4C plus 4. Use your equation to determine the number of marshmallows for 56 cubes. So M equals, we go 4 times 56 plus 4. So what's that? 224 plus 4 is 228. Okay. Your equation can also be used to determine the number of cubes you can make if you know the number of marshmallows you have. So now we know we have 460 marshmallows. So I'm just going to copy the equation out here. So I'm going to put 460 marshmallows in, and now we need to solve for C. So this is, you've done equations like this. This is something in IB Math we expect you to know, well, in regular math 10C as well, but this should not be a problem for you. So that's going to be 456 equals 4C. So C, we're going to divide by 4, is 114. Okay, number 13. Let's look at another relation, or same objects, but another relation between them. So let's now look at the relation between the number of toothpicks and the number of cubes. Use the diagram in your patterning skills once again to represent the relation as a table of values. So we know the number of cubes, we've got 6 of them, and how many toothpicks are required for each. So let's go back to our first diagrams here. So here, now the number of toothpicks, if you think about the left, well, you can think about the front like we did. 4 marshmallows, there's also 4 toothpicks. The back, there's 4 toothpicks, but now there's 4 that join those front and back together. So really, there's 12 toothpicks. Here, adding another cube on adds another 4 there and another 4 in between. So it adds 8. So there's 20. And then another 8 on that is 28. Another 8 on that is 36. So that's the pattern. Each time you add a cube, you're adding 8 toothpicks. Oops, sorry, gotta go back here. Okay, so what did we say? We started with 12, and then we had 20, and then 28, and then 36. And then following that pattern, add 8 would be 44, and then 52. So represent it as a set of ordered pairs. So there's your set brackets, 1, 12, 2, 20. Remember, ordered pairs have to have round brackets, okay? Really, I think they're called parentheses. Can't just leave them without. And so we might be a little bit picky about that on a test. If you give me all the ordered pairs but no brackets, you're going to lose half a mark. In some sense, depending on how many marks the question is. Okay, so be aware of that. Okay, that's the set of ordered pairs that represents the relation. In terms of the domain, again, we're just keeping it to 6 cubes. So the domain here is just 1, 2, 3, 4, 5, 6. And then the range is all of the toothpick values. Okay. Next one, represent as an arrow diagram. Might be able to do an oval here. Let's try this out. Yeah, there we go, there. And another one there. Okay, and then, so we have 1, 2, 3, 4, 5, 6. We have 12, 20, 28, 30, 20, 28, 36, 44, 52. And then just straight arrows across. Okay, and this is your cubes, and this is your toothpicks T. Then graph it. So here it started some of the scale, so 5, 6. Here it is not labeled for you, so we have to figure out, we have to go up to 52. So it'd be nice if some of our values landed on a grid line, but it may not happen that way. Let's see, so 1, 2, 3, 4, 5, 6, 7, 8, 9. So if we did by eighths, we'd have more than enough. But by eighths, actually, they wouldn't necessarily show up. Well, let's do, so you might want to do, yeah, I think I'll go eighths. So 8, 16, 24, 32, 40, 48, 54. Okay, so we can get it all in, all equally spaced. This is the number of toothpicks. Okay, this is the number of cubes. Okay, so then our order pairs, you can just go to the arrow diagram or you can flip back. So 112. So 112 is going to be halfway in between there, right? 220 is going to be halfway in between. 328 is halfway. So it's basically each of these is halfway in between, which is decent. If you went up by 5s, then it wouldn't be, at least this is easier to graph. If you went up by 4s, you wouldn't be able to fit all of it in. Okay, so same thing here. I'm not going to join them up with a line because you can't have part of a cube. Write a rule that relates the number of toothpicks to the number of cubes by completing the following statement. Okay, so again, I like to look here. Okay, if my table of values is, this is increasing by 1 each time. What's happening here? I'm increasing by 8 each time. So that means I'm going to have 8C, and then I have to figure out what to add or subtract to that. So 1 times 8 is 8, but I need 12. So I need to add 4. Does that work in all cases? So 8 times 2 is 16, plus 4 is 20. 3 times 8 is 24, plus 4 is 28. If it's a linear relation, that's going to be what you can do in all of them. So we take the number of toothpicks T, if we need that, we take the number of cubes and multiply by 8, then add 4. And then in terms of a equation, it'll be 8C plus 4. The number of toothpicks for 36 cubes what's that? 240 plus 48, 288 plus 4 is 292. And then number of cubes, okay, I'm going to copy out the equation. And I'm going to substitute in the number of toothpicks. Then I'm going to subtract 4 from both sides. And then divide by 8. And then C will equal, that's going to be 2, 36, 4, 5, 245. And we're done.